Hello friends, in the previous lectures we have been looking into what a gradient is and how it is relevant to materials research. Now one of the straightforward use of gradient is to understand the Fick's first law. So even though the Fick's first law helps us rather gauge how a flux would be in an heterogeneous system, the understanding of gradient helps us rather predict what would be the direction of the flux that is introduced when there is a inhomogeneity in the distribution of concentration. So the understanding of gradient as or treatment of the gradient as a vector helps us understand what would be the direction of the flux when there is a difference in the concentration according to the spatial position. So we will be able to understand, in addition to that conceptually a flux will be introduced, we will be able to understand in which direction this flux will flow, and correspondingly we will be able to understand what would be the direction along which a given phase would grow. So this is something that we saw in our previous lecture. Now that we have understood how a gradient works or how the gradient operates for a given variable or on a given variable, the accurate description of the Fick's first law would be of this form: minus of nabla d c of x, y and z. Now assuming that the d is constant, we can take the d, that is the diffusivity, out and we can express it in this manner. Now supposing you have a system where even the diffusivity, it varies with the position. It could happen that your system is present within a nuclear reactor, and when it is present in the nuclear reactor, the entire matrix is rather complete, it is constantly bombarded by high energy particles. So in that case there might be a deformation or a local deformation that the matrix experiences, so therefore the diffusivity depending on the position would vary. So therefore in those cases we have to go for the accurate description of the Fick's law. In those cases would be of this form here. However, for a generalized system, for our common system or in the Morse system, when the diffusivity does not significantly vary with the spatial position, then in those cases the Fick's law will be of this form here. Now often, depending on which textbook you refer to, this nabla is might be included with a vector notation above, and it is just to indicate that what we are essentially doing is we are taking the gradient of a scalar parameter, and through this operation, that is the gradient of a scalar parameter, what we end up having would be a vector. So in order to indicate that, we have such a depiction here. Now the skeletal form of this nabla, that is grad, we saw it can be written as I, one of the bases, plus j, or the skeletal form will not include any variable, so it will be of this form: j dou by dou y and k dou by dou z. So this is just a skeletal representation of what a gradient function is or what a gradient operator is. Now this is possible, that is we are able to remove d or decouple d from its association with concentration, is because this operator is rather a linear operator, and when this grad is imposed to, when we have a grad of two functions, that is f of x, y and z, plus g of x, y and z. So when we have such a function and we want to take the gradient of such a function, we can express this as grad of f of x, y and z plus grad of f of or g of x, y and z. So even though what is required is to consider the gradient of the coupled function or the combined function of f of x, y and z and g of x, y and z, since the gradient is a linear operator, it is possible for us to split it into two. So it is possible for us to consider the gradient of each function separately and add it up together. Now again, one way, so a way the grad is represented is in this manner with a vector notation, or just in this way using a nabla, or it is written as grad in this manner. Now in addition to this, we saw in our previous lecture that this gradient of a given function can also be extended to a set of data points. And supposing you have a set of data points that extends from 1 to n. So you have an independent variable 1, to so on and so forth, and it extends up to n, and you have a function that depends on all these independent variables. Now it is possible for us to rather estimate the gradient of this dependent variable. So it is possible for us to estimate the gradient of the dependent variable, provided we know how this dependent variables vary with respect to x, or x1 vary with respect to x2, and so on and so forth, and how it varies with respect to xn. So if we are able to estimate it, then it allows for us to estimate the gradient of this independent variable with respect to these dependent variable. Now, when we consider the representation of this vector in a vectorial space, what we essentially need is we need an n+1 dimensional vector space. The reason we need to have an n+1 dimensional vector space is because we have n independent vectors and one dependent vector, and we need to include all these in a vector space. So we need an n+1. So this will contribute to rather n dimension, and this will contribute to that of the +1 dimension. So essentially what we need is we would need an n+1 dimensional vector space. So this is the vector space that we needed when we want to describe, or rather graphically represent, how the concentration of carbon and manganese will influence, or how it will relate or influence the yield strength of a given mild steel or a given manganese steel. So if Y is the yield strength of a given manganese steel, and it depends on the concentration of manganese and carbon, so it is represented in this manner. So graphically it can be represented in this manner. So we can also consider this to be a vectorial notation if we treat this data set as a vector, because this will involve, when you consider several data points, this can be treated as several data points can be represented, or several concentration and the corresponding yield strength can be represented as individual data points in this vectorial space, and it is possible because we are able to create such a coordinate system. We are able to create such an orthonormal basis. So it means when I want an n+1 dimension, I should be able to create sufficient number of, there should be a sufficient number of bases present for me to represent it in the form of a vector. So therefore, when I have a set of data points which involves several independent variables and several one or numerous dependent variables, it is possible for us to estimate the gradient of it. And when we want to express the gradient of it, we need to have the sufficient number of indices to develop the basis. To develop that orthonormal basis, to have that orthonormal basis, we need to have sufficient number of indices. So this I, J and K in case of the three-dimensional vector space, which is what we refer to as the indices. Of course, there are different types of indices. We will get to that eventually, but for the current understanding, these are referred to as the indices. And now, depending on the nature of the data set that we handle, depending on the nature of the vector space that is required to rather indicate or accommodate this data set, the number of indices would vary. The number of indices which contribute to the basis, it varies, or we need to have sufficient number of indices to accommodate or to construct the required vector space that can accommodate the different data points. Now, the reason why we need to consider indices and bases is primarily because only when we are able to accommodate this, only when we are able to rather estimate or find the gradient of these data points, we will be able to efficiently handle all these data points. Now, one way of handling this data points as a data points itself could only lead us to such a certain extent. Now, if we translate it, if we handle it in the form of a vector, then all the operation that can be extended to a vector can also be extended to this data point. And one such operation is what we have seen here. So one such operation is the finding the differentiation of a vector or finding the gradient of. So even though we treat this as a scalar points, it is possible for us to find the gradient of these points. And ultimately, in the previous lecture, we saw that it is possible for us to optimize the function, and then this optimization plays a key role when we want to rather find what would be the composition that is required for me to get the specific yield strength. So often, when we develop a predictive model, we consider the concentration, and from the concentration we would like to predict what would be the corresponding properties. Now, the machine learning can also be used to do the reverse of it, wherein we want a specific property, and for that specific property we desire a specific property for an application, and we need to know what is the composition that could give me the specific property. It can be composition and it can also be processing parameters. So we need to know what is the combination of the concentration and the processing parameter that would give me this specific property. So for that we need to involve optimization, and for optimization, handling, or rather guiding the gradient of these data points are important. And if we want to find the gradient of this data point, if we want to handle these data points in a vector space, we need sufficient number of indices and corresponding bases. Now, when you consider, so these are the rather a recap of what we have been looking into in the previous lecture. Now, if you could recollect, the Fick's law doesn't stop with rather describing the gradient or just the flux that is introduced when you have a heterogeneous system. The flux, or rather the Fick's law, does not confine itself with this expression wherein it just states or discusses about the flux that is introduced in the heterogeneous system. However, so this is what we often refer to as the Fick's first law. Now, the Fick's second law, it builds on it, and it talks about the rate or the the rate at which, the speed at which the concentration evolves. The rate of change of concentration with respect to time is what is rather expressed in the Fick's second law. So the Fick's second law, when you consider the generalized representation of it, it is often represented by in this manner. So this is the generalized representation of what we have as, or when you just search for Fick's second law, it is how the Fick's second law is rather expressed. Now, the way we have arrived at it, even though it appears to be an accurate representation of the Fick's second law, we don't really, or the way we arrived at is rather different from the Fick's first law. In the Fick's first law, what we have essentially done is we have considered the gradient of the concentration, and since we have considered the gradient of the concentration, it has yielded a vector. Now, the Fick's first law, what essentially the Fick's first law is done is, in the Fick's first law, we have the output of the Fick's first law is a vector. Now, this output is treated as the input for the Fick's second law. So, in the Fick's first law, we consider the gradient of the concentration. When you consider the gradient of the concentration, it yields a vector, and this vector can be represented in this manner: J vector and K. So this is how, or this is rather the variable component of the Fick's first law. Now, when you consider the Fick's second law, the way the Fick's second law is written as the change in the concentration with respect to time, the temporal evolution of concentration. So the change in the temperature of concentration with respect to time can be considered as, or can be expressed as, temporal evolution of concentration. So how concentration changes with time is often referred to as the temporal evolution, and this is rather proportional to the, here a new operator is being used, the divergence of, so negative again for the convention, so negative of the divergence of the gradient of the variable. So what we have is, in case of the Fick's second law, what we do is we treat the output of the Fick's first law as the input, and correspondingly we estimate the temporal evolution of the concentration. So this is nothing but the output of the Fick's first law, and we treat it as the input for the Fick's second law and consider its divergence. So what essentially divergence means is that the divergence means the dot product of a divergence operator to that of an existing vector. So when you have an operator, the nabla operator, which is written as the skeletal form of it, which we have already considered. When you take the dot product of this operator with respect to another vector, then what we are essentially doing is we are considering, or we are estimating, the divergence of a vector. So you have nabla and we have a skeletal form of it, and when the nabla is used, or when this skeletal form is used on a scalar, when this skeletal form nabla is used on a scalar, we refer to it as the gradient, and the output will be a vector. And now this nabla, when it is used to, or when it is used in the context of a dot product, when the nabla is used as or it is treated as a vector and it is used to or used in the or used along with a vector, and it is operated or it is combined used as a dot product, then what essentially we are doing is we are coupling this nabla operator to that of a vector. So whenever we say that the divergence is associated with dot product, what we implicitly assume is there is another vector involved. So we will be able to use the divergence only in the presence of another vector. We will be able to apply this divergence operator on another vector, because the divergence essentially involves considering the dot product between this operator here and another vector. Now in the case of Fick's second law, that is exactly what happens. What essentially we have is we consider the dot product of this operator here to that of the output of the first law of the Fick's. So we consider the dot product between this skeletal operator here to that of the gradient of concentration. So again, the gradient of concentration gives us the desired vector, that is the flux, that is proportional to that of the flux, and we are taking the divergence of the gradient of concentration. When I say divergence of the gradient of concentration, what essentially we mean is we are considering the dot product of this operator to that of the vector, and that vector is gradient of concentration. Now when we consider the dot product of two vectors, ultimately the output would be a scalar, because essentially we are multiplying the components of these individual entities. So we are multiplying the components of these individual indices. So when you consider the dot product that is associated with the Fick's second law, what it essentially means is we are considering the skeletal form of the divergence here. This is the skeletal form of the divergence, and we are considering it along with, or we are considering the dot product of it with respect to the gradient of our concentration, which is dc by dx plus j vector dou c by dou y plus k vector dou c by dou z. Now this can be handled as, so this is nothing but, this here is nothing but the gradient of concentration, which is a vector that is part of the, or that is the output of the variable component of the Fick's first law. Now when you consider the dot product of these two, the end or the output of the Fick's second law would be, you can multiply, or all that we need to do is couple these two and multiply these two, and when we do that, what we end up having is dou square c by dou x square plus dou square c plus dou y square and dou square z by dou z square, and ultimately this is what we can be represented as nabla square c. And since in the Fick's second law, that is the temporal evolution of concentration is proportional to the divergence of the gradient of the concentration in an heterogeneous system, what we ultimately end up having is the, again there is a negative sign which we should not forget, it comes from the convention. This is again equal to minus of the second derivative, or the second double derivative of the concentration with respect to the individual spatial coordinates. So this forms the basis of the second law of Fick's second law. And again, if we include the constant of proportionality, if we include the diffusivity, and again if we consider the negative signs that comes from the gradient of concentration, that negative sign that comes from the gradient of concentration, it turns this negative sign into positive, and ultimately after introducing the negative sign that comes from the gradient, that is the Fick's first law, and also introducing the corresponding constant of proportionality, which is diffusivity, the expression is written as the nabla square c. So this is the Fick's second law. So what essentially we have is, we have developed a vector, a flux through considering or by considering the gradient of concentration. So the gradient of concentration yields as a vector, and we are taking the dot product of that vector with respect to the skeleton, the nabula, and this is what we refer to as the divergence. Now the divergence involves primarily dot product of this nabula operator to that of a vector. So in generalized case, the gradient or rather divergence means it involves the dot product of the nabula with respect to any vector. It can be any vector. So this is the generalized description of the divergence. Now in the context of Fick's law, what we have considered is, since the Fick's first law has already yielded us a vector in the form of a flux, we are essentially considering, so the accurate way of writing the Fick's second law is in this manner, wherein we have minus dot product of minus t c x y and z. So this is rather the accurate way of expressing the Fick's second law, wherein we have the gradient term here and we have the divergence term here, and there is a dot product that is being explicitly stated. So this is the accurate way of describing the Fick's second law. Now if you could recollect, since the nabula operator, the skeletal form of it is in itself, the skeletal form of the nabula operator in itself is a vector. So again, this is how we represent the nabula operator. So this in itself is a vector. So there should not be any c associated with it. So this in itself is a vector. This can be represented as a column matrix of this form: dou by dou x, dou by dou y, and dou by dou z. Now the variable component associated with the flux, the vector that arises from the flux, that is of the form. So when you include the concentration C here, so this variable component, the vector that is associated with the flux, can be expressed as dou C by dou x, y vector, dou C by dou y, j vector, and dou C by dou z, k vector. So this is again another vector which can be represented as the column matrix of dou C by dou x, dou C by dou y, and dou C by dou z. Now when I want to arrive, so when we want to arrive by combining from this expression, that is from this to expression, when we want to arrive at an expression wherein you have the double derivative of concentration with respect to the spatial coordinates, from these two, that is from these two expression, when we want to arrive at this expression, what can be done is, particularly when we want to arrive at this expression here from these two expressions, this expression here from these two expressions, particularly when these expressions or when these vectors are represented in the form of a column matrix, what can be done is we can consider the transpose of this matrix here. So we can consider the transpose of the divergent matrix that will give us dou by dou x, dou by dou y, dou by dou z, and we can leave this matrix as it is. This is the gradient matrix. So this is the gradient matrix. So what essentially we have done is we have considered the transpose of the divergence matrix, the divergence column matrix, and we have left the gradient C matrix as it is. Now by multiplying these two, what we will end up having is we will end up having such an expression, the expression that indicates the dot product. So what essentially we have done is, instead of taking the dot product, instead of going or adopting a conventional approach of taking the dot product, what we have done is we have represented the divergence operator in the form of the column matrix, and we have represented the gradient vector in the form of a column matrix. So we have gradient of C, which is a vector, we have represented it in the form of a column matrix here, and we have the divergence operator which we have represented in the column matrix here. Now what we have done is we have taken the transpose of the divergence and we have left the gradient vector as it is, and when we multiply, of course, the matrix multiplication, what we end up having is, we end up having the expression that is similar to that of the dot product. So essentially, the dot product between vectors A and vector B can also be, when you translate this to the column matrix, is equal to A transpose B. So this is one way of representing the dot product or estimating the dot product. So what essentially in this case we have done is, we have represented the vector in the form of a column matrix, we have taken the transpose of the first vector, and then we have estimated the matrix multiplication, or we have introduced the matrix multiplication and multiplied it with respect to the another vector, which is the column of another, or which is the column matrix, and that gives us a product that is identical to that of the dot product. Now the reason we need to consider this transpose approach of estimating the dot product is because when we are coding, when we are rather calculating the dot products, when we are calculating the divergence of the gradient, particularly in our context, if we are considering the divergence of the gradient of concentration, and we are adopting a computational technique, we are solving it using a computation machine, then often the dot product is estimated by this approach here. So when you are using a computer to solve this divergence of the gradient, or if you are attempting to solve the Fick's second law numerically using a machine, then this is how the dot product is rather estimated. Now what essentially we have so far considered is, we have considered the relevance of the gradient, and the relevance of the gradient is it extends beyond the Fick's first law, and it also plays a critical role when we are considering the data analysis in the multidimensional data case. And now we have introduced a special operator, a different operator that is different from that of the gradient. This we refer to as the divergence, and divergence is involved only when we are handling another vector. So what essentially divergence does is, the divergence take the dot product of the nabla operator to that of another vector. So generally, even though in the context of the Fick's second law, we are taking the divergence of the gradient of concentration, we are taking the divergence of the output of the Fick's first law, the divergence of the flux, which is a vector. In general case, the divergence involves the dot product between the nabla operator and that of another vector. And finally, when we want to use the divergence using or solve any expression involving the divergence in using a computational technique, using a computational machine, then essentially the dot product can be extracted in this manner. The transpose of the first operator and multiplication of it with respect to the vector, the column representation of the vector. Now, there is another way of using the same operator, that is the same nabla operator. Again, it can be introduced with a vector notation above, because implicitly this operator it is associated with the unit vectors of the basis. So therefore it is as indicated earlier, some nodes they include this vector notation, particularly when we are considering the divergence of a given vector. This notation here makes more sense. Now what we have seen is, we have considered a operator, and we have rather imposed that operator onto a scalar. We have imposed that operator onto a vector. Now imposing an operator onto a scalar, so this is the operator that we are talking about, the nabla operator. We have imposed it onto a concentration, and this we refer to as the gradient, and the output of it was rather a vector. Now this nabla operator, we have imposed it onto a vector, and this vector can be any vector. So therefore let me treat it as the vector j, which again the complex j, which is the flux that comes out of the Fick's first law. So this dot product is what we refer to as the divergence, and the output of the divergence is a scalar. And finally, what we have now considered is, so we have considered directly imposing or taking the product of, you can say just taking the product of the nabla operator with respect to a scalar. That is something that we have done. Of course, this is not a constant, this is a rather a variable. So therefore there is a specific, we have looked into it, how the gradient is to be taken and why it is a vector. And in a similar way, what we have done is, now we have related this nabla operator to that of another vector, and the way we have related the nabla operator to a vector is by considering the dot product. Now It is also possible for us to consider, in addition to the dot product, the cross product of the nabla operator to that of the vector. Now we can go beyond the dot product and consider the dot product of the nabla operator to that of the vector. Now when we consider the dot product, all we need to do was consider the components associated with each of the bases, and then we have to multiply them. Now the framework of the dot product and cross product remains the same, even though the operators are different, even though the way, or even though the different components, that different vectors that we are multiplying are, or different vectors that we are combining are different, the nature of the product remains the same. We have already looked into how we have to handle the dot product between two vectors and how we have to handle the cross product between two vectors. Now in this case, instead of two vectors, we have a vector operator and another vector, and we are attempting to find the cross product of these two vectors. Now when you consider the cross product, what essentially we have is, we do it by considering we estimate the cross product by considering the determinant of the matrix. That matrix involves, at the first row it involves the basis, and in the second row the components of the first vector, and in the second row we have the components of the third vector. Now here, in order to avoid a confusion, even though the second vector, the components of the second vector are of this form here, the second vector, that is the j vector that we are considering, at least the variable component of it is of this form. To avoid confusion which might crop up while considering the cross product, or the cross product of this nabla operator to that of the vector, in order to avoid any confusions that might crop up, what we can do is, we can express this first derivative of concentration with respect to C as Cx, the first derivative of concentration with respect to Y as Cy, and the first derivative of concentration with respect to C as Cz. So then what essentially we have is Cy and Cz, because the vector experiencing the cross product with respect to that of the nabla vector can be expressed as Cx I vector, Cyj vector, and Cyk vector. So all these components are included in the second row. So it is similar to how you would take the cross product between two vectors. In the first row you have your basis, in the second row you have the components of the first vector, in the second row you have the components of the second vector. So first row you have your basis, in the second row the components of the first vector, in the third row you have the components of the second vector. Now what essentially can now be done is, we can express each of these components, that is the component associated, the cross product will then yield the component associated with the I vector as something like this, Cx, or rather it's quite incorrect, Cy Cz minus j vector dou by dou x Cx dou by dou z Cz plus k vector dou by dou x dou by dou y Cx Cy. Now what essentially we have done is, we have considered the cross product between the nabla operator and a vector, and this is how the expression, the output of this cross product can be expressed as. This cross product is what we refer to as curl. So when you consider the curl of a vector, what essentially it means is, we are considering a cross product between the nabla operator and that of the vector. So what essentially we have is, we have considered gradient, and the gradient, it yields a vector. And we have considered a divergence is a dot product, so it yields a scalar. And finally we have considered curl. The curl is a cross product, it yields a vector, because this is how we estimate the cross product of the cross product of the j vector, or the curl of the j vector. So we have considered, or we have seen, three fundamental operators that involves the nabla, that is divergence, gradient, and curl. And all the properties that are applicable to that of the vector products are applicable to these divergence, or depending on the nature of the product that we have, is applicable to the divergence and the curl. So in the direction of the curl, the direction on the scalar nature of the dot product all stems from the fundamental our fundamental understanding of the vector products. So even though it might be rare that we use curl in the material research, it is possible, or particularly when we are handling solidification, it does play a critical role, particularly when we are handling a solidification or a crystal growth when the fluid or the liquid, the molten fluid is rather flowing instead of being static. When it is flowing, the curl plays a vital role. So even though in the context of divergence or in the context of Fick's laws, even though the curl is not, it does not play an integral role, the curl does play a role when you are modeling, when you are considering a system as a phase transformation wherein the liquid state of a system plays a vital role. For instance, when you are considering the solidification, the two phases that you are considering, one is the solid phase, the other is the liquid phase. It is not necessary that the liquid phase is often static. When you have a setup wherein the liquid phase is dynamic, and in midst of this dynamic liquid phase there is a solidification occurring, then in that case the curl of the flux plays a vital role. So essentially we have considered these three different operators, and we have seen what is the meaning of these three different operators, the role it plays in the context of the Fick's laws and other roles, or in the generalized understanding of it as well. So one is the direct imposition of the nabula vector to that of a scalar. The output is a vector. The second is the dot product between the nabula operator and a vector. Because it's a dot product, we need two vectors. The output is a scalar, and the third one is the cross product between the nabula operator and a vector. So the first one would be a scalar, or rather the first one would be a vector, that is the gradient would be a vector. The dot product will then be a scalar, and finally the cross product will also, because of owing to the nature of the cross product, the output will be a vector. Now, like touched upon in the moments before, what we have is, when we are describing a vector, even in this case here, we have rather an implicit understanding of what this individual indices mean. So when we are considering a vector, and when we are expressing a vector, we have an implicit understanding of what these individual indices mean. Often these, in this case here, we are considering a three-dimensional space, and these indices, they align, or we assume that these indices, again we assume that these indices align themselves along the coordinate basis or the coordinate system x. So we have our coordinate system defined as x, y and z, and we often, again not only us, in most of the simplistic treatment of the gradient, be it divergence or be it curl, whenever we want to handle, whenever we want to express a vector, we often restrict ourselves. In the simplistic case, unless otherwise it is required for a simplistic discussion, we assume that these bases, they stem from this coordinate system here, and these bases, they align themselves with these coordinate system. The I vector, or the I unit vector, it aligns itself with the x-axis. The j unit vector, it aligns itself with the y-axis, and the k, it aligns with itself with the z-axis. So these unit vectors, they have a meaning associated with it because we have assumed it in such a way. So this is what we refer to as the Cartesian coordinate system, and since we are considering these vectors in the Cartesian coordinate system, we have attributed a meaning to each of these indices. So what it essentially means is, whatever meaning this has, whatever meaning these individual indices has, it depends on to which coordinate system we relate it to. Let me repeat, in most of the simplistic cases, we consider these three vectors, these three unit vectors, to describe the direction of a given vector. In most simplistic cases, we use these three indices to describe a given vector, and often we assume that these three indices they lie along the direction of the coordinate system, they lie along the axis of the coordinate system. We describe a vector, we use three indices. So simplistic case, in most cases, we describe a vector, we use three indices, and these three indices, we assume that they lie along the axis of the coordinate system. And this coordinate system, we refer to it as the Cartesian coordinate system because these coordinate axes are perpendicular to each other. So whatever the meaning of these indices, they depend on the coordinate system that we adopt. Now, if we adopt a different coordinate system, correspondingly the meaning associated with these indices, it varies. So what essentially we are doing is, when we are representing when we consider such conventional representation of a vector, what essentially we are doing is we are attributing a meaning to it. We are implicitly assuming that these indices, they have a specific direction associated with it, and this specific direction is given by the coordinate system that we consider. However, unfortunately, Cartesian is not the only coordinate system that we have. So we also have polar coordinate system. We also have the three-dimensional extension of this spherical coordinate system, and we also have the cylindrical coordinate system. So what it essentially means is, depending on the nature of the coordinate system, the meaning assumed by the indices it varies. And on top of it, what we also have found out is, when we are considering the multi-dimensional vector space, it is rather not easy for us to conceive such a Cartesian coordinate system. So we saw that it is relevant for us to find, or it is relevant for us to consider the multi-dimensional vector space. And when we say we have a multi-dimensional vector space, imagining such a Cartesian coordinate system in a multi-dimensional vector space is not that straightforward. So therefore, we need to understand the meaning of these indices in different coordinate system, because when you consider a physical world, when you want to use these vectors, when you want to use the vectorial representation in the physical world, for instance, if you have the growth of a spherical precipitate and you have a specific direction of this growth, so the growth of the you are considering a growth of a spherical precipitate, and there is a specific direction along which this precipitate grows, and this growth is dependent on the flux direction. And this flux direction, when you consider the representing this flux direction or representing this flux vector, you might find that expressing this flux using a Cartesian coordinate system will be much easier than that of or using a spherical coordinate system will be much easier when compared to that of the Cartesian coordinates. So we have practical cases wherein using a different coordinate system will make your entire numerical approach rather straightforward. So when you consider a different coordinate system, expressing the given vector would be rather straightforward. Handling it would be rather straightforward when compared to other coordinate system. So therefore, we need to understand what is the relevance, how one can define the indices based on that coordinate system. So that is exactly what we will consider in the subsequent lecture. We will brush up our understanding of the polar and so we will consider at least these two coordinate system. We will try to relate these two coordinate system, and we will try to arrive at an expression of vectors wherein the indices do not have an already well established understanding, but it has a contextual understanding. It has an understanding that is relevant to the problem that we have that we want to discuss about. Let me repeat the indices. As a conclusion, let me just try to tie up all that we have discussed in the final section of this lecture. So what we want to do is, instead of representing a vector using indices that is already established and that is tied up or that is rather restricted to the Cartesian coordinate system, we want to express the vectors using indices that are generalized, that are based or that can be employed for any coordinate system, that is not coordinate system dependent. So that is what we will be driving towards in the subsequent lecture. In order to do that, as a first step towards it, what we will essentially do is we will try to understand the polar and the Cartesian coordinate system, how one relates to another. So that is how we will be progressing in the subsequent lecture. Goodbye.